When laser optics operate under intense laser irradiation, they might eventually suffer from damage. The damaged optical element doesn't work as expected and cause multiple troubles in various laser-based systems. In order to avoid unexpected laser damage, optical elements should be tested before use. How to survive laser damage? There's several possible methods, and Raster Scan test is one of them. The raster scan testing of laser-induced damage threshold is intended for cases when optics performance is limited by localized defects. It was designed specifically to deal with large aperture optics. Let's see when and why it might happen. In this case, precursors of laser damage are defects embedded during optics manufacturing processes. Cutting is known to induce scratches and digs, polishing is linked to the formation of BLB layer, and nodules can form during the coating procedure. Such defects feature enhanced localized absorptance and thus are dangerous, especially for laser pulses with relatively long durations. Classical approaches of laser-induced damage threshold testing, such as the S-on-1 or 1-on-1, are all statistical. They are based on a matrix with isolated test sites, each irradiated by a small laser beam if compared to optic size. Thus, classical testing works well for classical optical elements when defect density is rather high. For high-quality or very large objects, the defect density is rather low. Accordingly, when using a small laser beam, there is a low probability to hit at least one accidental defect. This is a primary cause of why the laser-induced damage threshold is overestimated or not repeatable on large optics when using a classical test. The raster scan procedure should be applied in such cases. Let's discuss how the raster scan procedure works. A significant part of the optic must be considered for testing. Usually the 1 cm square is used, if not insisted otherwise. The intended test area is then mapped by a microscope in order to document all the apparent defects prior to laser exposure. Next, the laser is set to a low starting irradiation level. Power is usually monitored by the power meter. Let's mark the fluence level on the x-axis. Now the inspected area is uniformly scanned by moving the laser beam so that every point of the surface is covered with at least 90% of the onset peak irradiation level. The interrogated area is mapped once again and inspected by a Nomarski microscope. The density of the laser-induced localized damages is investigated. Let's mark defect density in the y-axis. If no laser-initiated damages are detected, density is marked as 0. The laser of the test system is now set to a higher irradiation level, and the same area is raster scanned again. The irradiation level is continuously increased while the same area is raster scanned again and again. In between of every scan, a microscopic analysis of the surface is performed to determine the damage density as a function of irradiation level. The process is stopped when the maximum irradiation level of the system is reached or defect-driven damage becomes catastrophic. Now, laser-induced damage threshold is estimated as the average of irradiation levels, corresponding to the lowest observed damage and the first undamaged level below. Various scenarios can be observed in practice. For example, some damages are barely visible and appear in form of small pinpoints. Let's call them damage initiators. At higher irradiation levels, small damages turn into larger craters. Let's call them catastrophic damage. The higher the irradiation level, the more objects become apparent. Also, their sizes tend to increase. By analyzing microscopic images taken before and after every new scan, it is possible to extract the sizes and densities of all the investigated objects. A figure displays the cumulative distribution of all objects found according to their density and size. Such data representation is providing additional information about the defect-driven damage behaviors until damage becomes catastrophic. There is also several risks associated with this procedure. As the laser irradiation level is ramped over the same area, laser conditioning, laser cleaning, or fatigue incubation effects are expected depending on chosen scan parameters. Accordingly, estimated LIDT values could differ from those estimated by other testing approaches. Nevertheless, the raster scan procedure, being most sensitive to defect-driven damage, is typically providing the smallest thresholds among all the testing procedures. The main application of the raster scan procedure is a worst-case scenario testing of samples with low defect density. This procedure is also widely used to test large optical elements, since there is no other way to minimize the risk of costly unexpected failure. Furthermore, it is a great tool to investigate defect density and laser damage growth. Thus, the raster scan application for LIDT measurements is gaining popularity every year. Contact Lidaris to learn more about raster scan testing and other ways to solve your laser damage problem.